Hey everyone, I'm here with your 124 lesson. What patterns can I find? Products, factors, and factor pairs. Do you ever hear people talk about the factors they consider when they make a decision? If you wanted to decide what movie to see, factors that could affect your decision might include who is in the movie, what the movie is about, and which movies are playing in the nearby theater. Factors that affect decisions are like numbers that affect a product. In mathematics, factors are numbers that create new patterns when they are multiplied. A number resulting from multiplication is called a product. In other words, since 2 times 3 equals 6, 2 and 3 are factors of 6. Well, 6 is the product of 2 and 3. Also, 1 times 6 equals 6, so 1 and 6 are 2 more factors of 6. Thus, the number 6 has 4 factors, 1, 2, 3, and 6. In this lesson, you will use an extended multiplication table to discover some interesting patterns of numbers and their factors. So today's lesson is a 2-day lesson. If you are missing day 1, we're going to be working through problems 173 through 177. If you're missing day 2, you want to fast forward ahead to the video to where I say that we're starting day 2, which is problems 178 through 181. So 173. Have you ever noticed how many patterns exist in simple multiplication table? Such a table is a great tool for exploring products and their factors. Get a lesson 124 resource page from your teacher. Fill in the missing products to complete the table. With your team, describe at least 3 ways besides simply multiplying the row and the column numbers that you could use to find the missing numbers. So on your resource page, which is, I just have to find it, hang on a second, right here, lesson 124, you want to work through problem 173. So go ahead and pause the video and do that. Okay, if you're back with me, you filled out your table and you have found some ways to find the missing numbers. 174. Gloria was looking at the multiplication table and noticed an interesting pattern. Look, she said to her team, all of the prime numbers show up only 2 times as products in the table, and they are always on the edges. Discuss Gloria's observation with your team. Then choose one color to mark all of the prime numbers. Why does the placement of the prime numbers make sense? So go ahead and work on this problem. So if you've answered this problem, hopefully from the introduction, you can also see that 1 times 6 equals 6, so 1 and 6 are factors. So when we have a prime number, we want to remember that it's the number times 1. So a prime number only has 2 factors. And 1 factor must be the number 1. So that's why if you're looking at the multiplication table, the number 1 column is all the way over here, so it would be on the edge. And you could have come up with something different, but as long as you support your answer, you will be good to go. 175, finding patterns. See how many patterns you can discover in the multiplication table. The suggestion in parts A through C below help you get started. Gloria's observation in problem 174 related to prime numbers. What other kinds of numbers do you know about? Begin by brainstorming a list of all kinds of numbers that you have discussed. You may want to look back at lesson 123 to refresh your memory. Where do these different kinds of numbers appear on the table? So what types of numbers have we discussed? Part B says, what patterns can you find in the locations of the numbers of each type? Be ready to explain your observations. And part C says, notice how often different types of numbers appear. Record your observations. Do you find any patterns that make sense? So go ahead and work through problem 175. Okay, if you're back with me, you've done problem 175. And remember, as long as you can support your answers, you are going to be good to go because what you say might be different than someone else. 176. Consider the number 36, which could have been Anne's number in part B of problem 162. Choose a color or design such as circling or drawing an X and mark every 36 that appears on the table. So do that. Imagine that more rows and columns are added to the multiplication table until it is as big as your classroom floor. Would 36 appear more times in a larger table? If so, how many more times and where? If not, how can you be sure? Okay, so you want to support that. So you should have said, yes, it would appear. Hopefully you figured out 4 more times. Okay, that could be 1 row, 36 columns. Oops, spelled that wrong. 2 row, 18 column. Then reverse 18 row, 2 column, and 36 row, 1 column. So now you're going to list all the factor pairs of 36. A factor pair is a pair of numbers that multiply to give you a particular product. For example, 2 and 10 make a factor pair of 20 because 2 times 10 equals 20. How do factor pairs of 36 relate to where it is found in the table? How does each factor pair tell you about the possible rectangular arrays of 36? How many factors does 36 have? So you're going to want to list the factor pairs. Go ahead and do that. Okay, if you're back with me, you've listed the factor pairs. So 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. So then you want to make sure, how do the factor pairs of 36 relate to where they are found in the table? And what does each factor pair tell you about the possible rectangular arrays for 36? So the factor pairs are the row and columns, right? 1 times 36, so 1 and 36. And the factor pairs also describe the length and the width of a rectangular array. So we could do 2 by 18, and that would be the length and the width of a rectangular array. How many factors does 36 have? Well, we can only count 6 once. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 factors of 36. And they are 1, 2, 3, 4, 6, 12, 18, and 36. Moving on to 177. Frequency is the number of times an item appears in a set of data. What does the frequency of a number in the multiplication table tell you about the rectangular arrays that are possible for that number? A. Gloria noticed that the number 12 appears as a product 6 times in the table. She wonders, should there be 6 different rectangular arrays for 12? What do you think? Work with your team to draw all the different rectangular arrays for 12. Explain how they relate to the table. So go ahead and work on part A. Part B says, how many different rectangular arrays can be drawn to represent the number 48? How many times would 48 appear as a product in a table as big as the classroom? Is there a relationship between the answers? So for part B, hopefully you came up with 5 rectangular arrays and 10 appearances in the table. So is there a relationship between those answers? C, in problem 176, how many different rectangular arrays should be drawn to represent the number 36? How many times did it appear as a product in a table as big as the room? Does the pattern you noticed for 12 and 48 also apply to 36? If so, why does this make sense? If not, why is 36 different? Okay. So think about that. Okay, that is it for day 1 lesson. So if you have any questions or want me to look at anything, please let me know. So now we're moving on to day 2, which is starting at problem 178. Prime factorization. What are all the factors of 200? So take a minute, pause, and list the factors of 200. Okay, factors of 200. 1, 2, 4, 5, 8, 10, 20, 25, 40, 50, 100, and 200. Part B says, a prime factor is a factor that is also a prime number. What are the prime factors of 200? So look back up at your factors and just name the prime factors. Okay, 2 and 5 are prime factors. C says, Sometimes it is useful to represent numbers as the product of prime factors. How could you write 200 as a product using only prime factors? Writing a number as a product of only prime numbers is called prime factorization. So we want, product is multiplication, remember? So we want to multiply those prime numbers to get 200. So what can we do? Go ahead and try. Okay. You should have had 2 times 2 times 2 times 5 times 5. In any order, that would have worked. Okay, you're still going to multiply to get 200. D, Tatiana was writing 200 as a product of prime numbers. She shared with her team the beginning of her work, which is shown below. 200 equals 4 times 50 equals 2 times 2 times 10 times 5 equals 2 times 2 times 5 times 2 times 5. Notice that Tatiana uses a dot to represent multiplication. This is a way to show multiplication without using the x. Try this method now so that when you learn algebra, you are not confused with the use of the letter as x as a variable. What process do you think was going through Tatiana's mind when she wrote 200 as the product of prime factors? So what was she doing? Okay, well, what do you notice each time she breaks it down? Each time she breaks it down, she is only using prime factors. So she's breaking down the previous step with factors. Do you think it matters what products Tatiana wrote in her second step? What if she wrote 10 times 20 instead? Finish the prime factorization using Tatiana's process. So we did 200, and that equals 10 times 20. You will need to finish that. Okay, go ahead and finish that. Okay, when you're done, we're moving on to 179. 179 is practicing prime factorization. So you're going to start with your equal signs, and you're going to break each one down with prime factors. Okay, I want you to try that on your own. When you're done, you're moving on to 180. When you write a number as a product of prime factors, often you have many factors to record. Explore this idea further in parts A through C below. How many prime factors did you need to represent part D of problem 179? So it depends what you did, but it's asking you prime factors. So you should have needed 6 prime factors. No matter which way you did the tree, you'll need 6 prime factors. To make it easier to record prime factors, you can use exponents. Do you remember how repeated addition can be written in shorter form using multiplication? For example, 10 plus 10 plus 10 plus 10 plus 10 can be written as 5 times 10. Similarly, repeated multiplication can be written in shorter form using exponents. 10 times 10 times 10 times 10 times 10 equals 10 to the 5th. Okay, that should say 10 to the 5th, not 105, 10 to the 5th. The prime factorization of 200 from problem 178 was 2 times 2 times 2 times 5 times 5. How could you write this with exponents? So go ahead and try. Okay, so hopefully you came up with 2 times 3 times, or 2 to the 3rd times 5 times 2. Let me rephrase that. I just said it wrong again. 2 to the 3rd times 5 to the 2nd. It's how many times the number appears. So again, 2 to the 3rd times 5 to the 2nd. Part C is asking you to write your answers from problem 179 in exponent form. So go ahead and work on that. So A should be 2 to the 2nd times 5 to the 2nd. B should be 2 to the 2nd times 3 to the 2nd. C should be 2 times 3 to the 3rd because 2 only appears once. And D should be 2 to the 3rd times 3 times 5 to the 2nd. Okay. Finally, the last question. 181. Why does it work? Work with your team to analyze an interesting pattern in the multiplication table. Explore using the multiplication table or your resource page. Choose any four numbers with the multiplication table that form four corners of a rectangle. For example, you could choose 6, 15, 14, and 35, as shown in the bold at the table at right. Multiply each pair of numbers at opposite corners of the rectangle. In this example, you would multiply 6 times 35 and 14 times 15. A, what is the pattern? Work with your team to test enough examples to convince you that there is a consistent pattern. And B, why does the pattern work? Work with your team to explain why it makes sense that the products of the opposite corners of any rectangle in any multiplication table are equal. So I want you to work through A and B. That is the last two questions. And remember, support your reasoning here. Okay, some people could have different ones. You're going to have different rectangles, but you want to make sure you support your reasoning. So that is it for the lesson 1, 2, 4. Remember, this was a 2-dayer, so you only needed to do day 1 or day 2. If you have any questions or would like me to check over anything, please let me know.